not than fire. So we thought it might be useful, just for the purpose of discussion, if I would try to write down all the advantages of going to higher energy, and then people can react. You can react to them or add some more if I've forgotten them. So just to remind you, what we're talking about is going from 3 to 6 MeV per nucleon at the top energy, depending on the mass to charge of the beam. So for n equals E, it's 6 MeV approximately for ReA3 to 20 MeV or a little bit above. That's shown here. So a little over 20 MeV for n equals E, and up to 12 MeV for uranium. So it's this energy upgrade from the 5 MeV to the 20 MeV range. And of course, eventually, as Georg said, this becomes part of FREP. As part of the ReA12 upgrade proposal for FREP, and what we would want to include as soon as possible, is the addition of additional more than 13,000 square feet of floor space. And so the idea would be to add a high bay that would cover roughly this area, and just as a thought process, as Georg said, what kind of experimental equipment would fit in at least part of this. It looks something like this. Okay, so why would you want to do this? Well, why do we want to go to 12 to 20 MeV per nucleon? Well, this is nothing new. Actually, the user community has sort of consistently made this case that reaccelerated beams should go up into this energy range, and I just remind you of some of the documentation supporting this, and going back even to the earlier days of this discussion of reaccelerated beams. Now, so it's something the user community has consistently made the case for. Specifically, it provides more space for experimental programs, and I think very significantly, the sooner that this can be implemented, the sooner it allows users to begin to put their equipment on the floor, shake down the equipment, and to begin the scientific programs. And it's better for the science of FREP if this happens as soon as possible. So a lot of the discussion Philomena stimulated about studying the reaction mechanisms and trying to find ways to extract these spectroscopic factors. Obviously, this is a good thing to have developed before we start FREP, and we really want this information to understand how the structures evolve. We want the techniques to extract the structure. So it's this shakedown of equipment, and also, in a sense, the shakedown of the science programs. And, well, the main reason, actually, is, of course, the expanded scientific capabilities that this will offer. And I'm just going to quickly try to highlight those in the bulleted form in the next couple of slides. So generally, the mantra is to go to ReA12 would get us above the Coulomb barrier for all beams. So why is that interesting? Well, as Philomena was saying, so this gives a vast improvements in transfer reaction studies and extension of the kind of the neutron transfer studies that are being done now, are possible now for mid-mass and light nuclei up to the heaviest nuclei. The higher energy would allow one to study broader range of excited states. So if you want to study splitting of strength, you'd like to look at a broad range where p-values become more negative and you need the higher energy. Generally, this is kind of general statements, but you'll have better L-value selectivity in the transfer, and as Philomena was discussing, perhaps with the higher energy beams, we can develop techniques to provide better spectroscopic information for nuclear structure studies. Often the kinematics become more favorable for particle detection, and again, a wider energy range allows you to study this energy dependence and try to figure out really the optimum way of extracting the information that you want to extract. And of course, these same arguments we make for DP, even more so go if you're doing alpha or helium-3 induced reactions where you'll need the higher energy to do these studies, certainly 10 MeV or higher. Now, there are other things besides transfer there's a chance to use deeply inelastic reactions, multinucleon transfer, and something like going above the 5 MeV range up to 15, and I'll make an argument maybe even 20 is interesting. So this potentially opens up the possibility, if you can use deeply inelastic reactions, to study even more neutron-rich particles in your beam and produce them in a wide range of states and study their gamma decay. The higher energy looks like it's going to be very important and interesting for Coulomb excitation, certainly multiple Coulomb, even single Coulomb. And if you wanted to start a program of unsafe Coulomb, like it was done argon for heavier beams, you would certainly need the higher energy. And for single and multiple Coulombs, in fact, as you go to higher energy, you'll increase your sensitivity by more than a factor of 10. And I'll show an example of that in just a second. Anyway, sorry, this continues. So if you want to begin to study cluster transfer, particularly two particle transfer, these Q values tend to be negative, and you simply will need the higher energy to do those studies and try and get sensitivity. The programs that use surrogate reactions are done in the 10 MeV per nucleon or higher range. And I'll just remind you of the work that's done by the Berkeley, Livermore-Rutgers collaborations, where they're looking to study neutron-induced fission at equivalent neutron energies, and those are done even in the above the 10 MeV per equivalent, 10 MeV, 15 MeV per nucleon equivalent. The Texas A&M group and others have done really interesting work on developing ways of extracting these A and Cs from reactions, and they would like to do them in a regime where they have reliable optical model parameters that they can extract from the way that they extract the JLM techniques, and that needs also this higher energy, 10 or so MeV per nucleon. If you want to employ the Trojan horse technique to try to infer important astrophysical reaction rates, as is done and proposed by, for example, experiments in Catania, then again you need to be above the Coulomb barrier, and again that will require the higher energy. It came up a little bit today earlier when we were discussing the R process. There are ideas on how you can study fission and extract fission barriers, but again that needs to be done by studying fission induced at a range of energies, and by studying over a range of energies from 5 to at least 20 MeV per nucleon, and perhaps even